4.5 billion kilometers from the Sun, in a darkness that no human eye has ever directly witnessed, a planet turns. It is not a fast turning. Neptune completes one slow rotation every 16 hours or so, its cloud-banded face sweeping through a dark so complete that the Sun itself, to seen from that distance, is only the brightest star in a field of stars, a point of cold white light, brilliant but small, casting illumination too thin to warm anything. The light that reaches Neptune has already traveled for more than 4 hours. It arrives diminished, stretched thin across the vast difference between the inner solar system and the outer dark, and what it falls upon when it finally arrives is a disk of color that seems at first almost impossible. Neptune is blue, not the pale, washed-out blue of a winter sky, not the shifting green blue of shallow ocean water, but a deep saturated cobalt, a color so pure and so densely itself that images of the planet taken by spacecraft look almost artificial, like a painted sphere rather than a world. And the reason for that color is precise. It is not accidental. It is not produced by an ocean or a sky in any ordinary sense. It is produced by a single kind of molecule, methane, quietly absorbing the red wavelengths from what little sunlight arrives and sending back only the blue. The methane in Neptune's outer atmosphere acts as a filter, selectively removing warmth from the spectrum and returning cold blue to space. Every image ever taken of Neptune, every shade of that extraordinary cobalt, is the visual record of a chemical process happening in the outermost layer of a planet that no human being has ever visited. That outer layer, the cloud tops, the visible face, is where the story of Neptune begins. Not because the surface is interesting in itself, but because it is the only part of the planet that light ever touches. Below the cloud bands, the darkness is not the darkness of space, which at least admits starlight. It is something else. Below the clouds, the darkness is the darkness of the interior, sealed in, pressurized, unmixed with anything from outside. And the interior of Neptune is where everything that makes this planet genuinely strange is waiting. The cloud tops hang at the outermost edge of an atmosphere composed mostly of hydrogen and helium, with methane woven through it in smaller proportions, a few percent by volume, enough to blue the entire planet. The winds at this level are among the fastest measured anywhere in the solar system. They are not gentle, they are not warm. The temperature at the cloud tops hovers around minus 200 degrees Celsius, a cold that would end most chemical activity entirely and freeze most known gases into solids. And yet Neptune, sitting at the edge of the solar system, storms. Great dark ovals form and dissolve in its upper atmosphere. Bright white clouds of methane ice drift along the equatorial bands. The planet is active in a way that is difficult to account for given how little solar energy reaches it, a detail that will settle slowly into significance the deeper this descent goes. Below the clouds, the atmosphere thickens. This happens gradually, across a transition that has no clean boundary, no visible line where the gas stops being a gas and becomes something else. The pressure simply increases, temperature rises, the hydrogen and helium grow denser, and the layers of the atmosphere press more heavily on the layers below them. The descent is not dramatic in the way that descending into an ocean might be dramatic. There is no surface to break through, no sudden change in resistance. There is only the slow, unceasing addition of weight. Kilometer by kilometer below the cloud tops, the pressure climbs, and the nature of the matter being pressed on changes in response. A few hundred kilometers below the uppermost clouds, the atmosphere has already transformed. Methane molecules that were drifting freely in the thin upper air are now part of a much denser medium. The temperature, which was bitterly cold at the cloud surface, begins to climb as the surrounding pressure compresses everything. This is a simple physical consequence of compression. Matter under increasing pressure tends to warm because the energy of that compression has to go somewhere, and it goes into heat. Neptune's interior is not cold. That is one of the first things that careful distance from the planet's surface changes. What appears from the outside as a frozen, remote, cold blue world is in its interior genuinely hot. The cold is only skin deep, if skin can be said to exist on a world with no solid surface to speak of. Somewhere between 300 and a few thousand kilometers below the cloud tops, the composition of the planetary material begins to shift in a way that marks a genuine transition in the planet's structure. The hydrogen and helium of the outer atmosphere give way, not abruptly, not with any signal, but over a gradual depth range, to a different mixture. Water enters the picture. Ammonia, methane, still present, but now under pressures and temperatures that begin to strain its molecular bonds. These three compounds, water, ammonia, and methane, are the defining materials of Neptune's deep interior, and they mix together into something that has no clean name in the vocabulary of ordinary experience. Scientists call this layer the ice mantle. The name is misleading in almost every meaningful way. Nothing in this layer is frozen. Nothing in it is ice in any sense that connects to the texture of ice on a winter morning, or even to the ice of distant comets. The ice and ice mantle refers only to the chemical composition. Water, ammonia, and methane are the same compounds that exist in solid form in the outer solar system as actual ices accumulated in comets and the surfaces of distant moons. But inside Neptune, under the conditions that reign at these depths, they are not solid, they are not cold, and JT, they are a hot, dense, pressurized fluid, a mixture that flows and compresses in a state that physics describes with terms like superionic and plasma-like, terms that gesture toward matter behaving in ways that have no ordinary parallel. The ice mantle of Neptune begins at roughly 3,000 kilometers below the cloud tops and extends inward to somewhere around 15,000 kilometers. That is a layer, a single structural region of a single planet with a depth greater than the diameter of Earth. The entire width of this planet, from surface to far surface, passes through inside this one layer. The scale of it is not easy to hold in mind. A descent through the ice mantle of Neptune would cross more distance than the full width of Earth, and it would cross it through conditions that grow progressively more extreme with every kilometer traveled downward. At the top of the ice mantle, where it grades gradually from the denser lower atmosphere, the pressure is already far beyond anything achievable in ordinary laboratory settings. At the base of the ice mantle, the boundary with the planet's rocky core, the pressure is estimated at somewhere between 6 and 7 megabars. A megabar is 1,000,000 times Earth's atmospheric pressure at sea level. 6 megabars is 6,000,000 times that pressure. The weight of the entire planet above presses down on the material at that depth with a force that compresses molecules to a fraction of their ordinary size, that strips electrons partly loose from their atoms, that creates forms of matter that have no analog anywhere on the surface of this or any other planet reachable by human experience. For most of human history, the existence of Neptune was unknown. It was not seen until 1846. Even then, it was not seen so much as mathematically expected, predicted by the gravitational disturbances it created in the orbit of Uranus, the planet just inward of it in the solar system. Neptune made itself known by the way its gravity pulled on things before any instrument had resolved it as a disk. That act of indirect inference, knowing something by its effects before the thing itself is visible, is a fitting introduction to a planet whose most important structures are entirely hidden from view. Almost everything that makes Neptune what it is lies in layers no spacecraft has ever entered, and no instrument has yet directly measured. The only mission to visit Neptune was Voyager 2, which flew past in 1989, a single pass at close range, an extraordinary achievement that returned the first clear images of the planet and its moons and provided the first real measurements of its magnetic field and atmosphere. But Voyager 2 did not enter Neptune's atmosphere. It did not descend. It skimmed past at a distance. Its instruments pointed at the cloud tops and the surrounding space, and then it continued outward into the dark beyond the solar system. Everything that is known about Neptune's interior comes not from direct measurement, but from modeling, from calculations that work backward from the planet's overall mass, its size, its gravitational field, and its heat emission to infer what must be inside. Those inferences paint a picture of a planet structured in concentric shells, each one defined by the particular state of matter appropriate to the pressure and temperature conditions at that depth. The outermost shell is the atmosphere, the cold blue methane bearing hydrogen and helium visible from space. Below it, the ice mantle of superheated fluid, water, ammonia, and methane mixed and compressed into something unlike anything in ordinary experience. And below the ice mantle, at the very center of the planet, a core of rock and silicate material, probably iron and magnesium-bearing minerals, the same fundamental materials that make up the interior of Earth, though compressed to densities and temperatures that would transform them well beyond any recognizable form. The core of Neptune is estimated to reach temperatures of around 7,000 Kelvin. That is hotter than the surface of the Sun. The surface of the Sun, the bright disk of light that produces all daylight on Earth, burns at roughly 5,500 Kelvin. The center of Neptune, a planet in the outer darkness of the solar system, is hotter at its core than the surface of the nearest star. This is one of the ways that Neptune defies the intuition that comes from knowing it only as a cold blue point of light. The cold is the skin. The interior is another thing entirely. The classification of Neptune as an ice giant is in one sense a statement about composition rather than condition. Jupiter and Saturn, the largest planets, the gas giants, are made mostly of hydrogen and helium. Their interiors are dominated by these lightest elements, compressed under their own enormous gravity into exotic metallic and liquid states, but still essentially hydrogen and helium all the way down. Neptune and Uranus are different. Roughly 80% of their mass consists of compounds built from oxygen, nitrogen, and carbon bonded with hydrogen, water, ammonia, methane, and related molecules. These are the ice-forming compounds of the outer solar system. They are called ices by planetary scientists, regardless of their actual phase, because that is what they are in the cold reaches of space, where comets and distant small bodies accumulate them. Inside Neptune, under the conditions prevailing there, they are no longer cold, they are no longer solid, but they are still the same molecules, or rather, they are those molecules under stress so extreme that the molecules themselves begin to change. Methane is a carbon atom bonded to 4 hydrogen atoms, a compact, stable molecule at the pressures and temperatures of Earth's surface. At the top of Neptune's atmosphere, methane is still methane in the ordinary sense. It drifts in the cold upper air. It absorbs red light. It scatters blue. But methane, transported downward, by convection currents, by the slow churning of a fluid planetary interior, is methane moving toward conditions where its ordinary stability fails. The bonds holding the carbon to the hydrogen atoms were designed, in a manner of speaking, by chemistry for the conditions of moderate pressure and moderate temperature. As pressure climbs and temperature climbs with it, those bonds come under increasing stress. There is a threshold at which they will no longer hold, but that belongs to the deeper layers, to the pressures and temperatures below where this descent currently rests, in the upper reaches of the fluid mantle, where methane is still methane, but the conditions around it are already extraordinary. In the ice mantle, the fluid, that hot, dense, pressurized mixture of water and ammonia and methane, is not still. It is not a static layer, like sediment at the bottom of a jar. It moves. Convection carries hotter material upward and cooler material downward in a continuous churning motion that has been operating since the planet formed 4.5 billion years ago. The timescales of this circulation are not the timescales of weather or ocean currents. A single convective cycle in Neptune's mantle may take millions of years. The fluid moves with the patience of planetary time, a patience so deep that the concept barely translates into anything with human dimensions. The magnetic field of Neptune, measured by Voyager 2 and found to be both strong and geometrically peculiar, is believed to originate in the ice mantle. The motion of the electrically conducting fluid, water, ammonia, and methane under high pressure become ionically conducting. The electrons and ions in them move in response to electromagnetic forces, generates electric currents, and those currents produce the magnetic field. The field is strong, but tilted at an angle of nearly 47 degrees from the planet's rotational axis, and it does not pass through the planet's center. This geometry is unusual. Earth's magnetic field is also tilted from its rotational axis, but only by about 11 degrees, and it passes through or near the center. Neptune's field is offset and inclined in a way that suggests it is generated not in the deep core, but somewhere in the conducting mantle fluid, where the convective motions are most active. The planet's interior is dynamo and mystery in equal proportion. Light does not penetrate the cloud tops. Below the uppermost layer of atmosphere, Neptune's interior has been dark since the planet formed. Dark in the sense of absolute. No photon from outside has ever illuminated the ice mantle. No sunlight has ever reached the interior boundary. No light from any source other than the faint thermal glow of the material itself has ever been present in these depths. The thermal glow is real. Matter at thousands of Kelvin radiates light, infrared and beyond, but it is not visible light, and it illuminates nothing in the way a lamp illuminates a room. The interior of Neptune is in a darkness that the concept of darkness does not fully capture, because the darkness of a closed room at least has a history of light. The room was once open. The light was once there. Neptune's interior darkness has no such history. From the first moments of the planet's formation, the layers below the atmosphere have been sealed from light entirely. This permanent darkness presses on the imagination in a specific way. The ice mantle, that layer spanning a depth greater than Earth's diameter, is not only hot and compressed and continuously churning, it is doing all of this in total and permanent blackness, under pressures that would reduce any material carried there to something unrecognizable, at temperatures that exceed the surface of the sun, with no external reference point of any kind. It is an interior that has never been visited, never been directly observed, and may never be. The instruments that would be needed to probe it do not yet exist. The engineering to get them there and return data would require technologies beyond any currently in development. What is known about the ice mantle is known by inference, by modeling, by the careful application of physics to the numbers the planet reveals from outside. Its mass, its size, the faint signatures of its gravity, the infrared glow it emits. And it does emit a glow. This is one of the measurements that Voyager 2 confirmed, and that earlier observations had suggested. Neptune radiates more energy than it receives from the Sun, not slightly more, roughly 2.5 times more. The Sun provides a certain amount of energy to Neptune, diminished by the inverse square of the enormous distance, and Neptune sends back into space around 2.5 times that amount. The planet has its own internal heat source, something generating warmth from within that adds significantly to the modest solar input. The source of this excess heat is not definitively known, but the interior, the hot convecting compressed fluid mantle, is clearly involved. The planet is not just a cold object in the dark. It is warm from inside, radiating quietly into space, sustained by something happening in its hidden depths. The contrast between Neptune and Uranus, its near twin in terms of size and general composition, sharpens this observation. Uranus, similar in mass, similar in composition, similarly distant from the Sun, does not radiate significant excess heat. It emits roughly the same amount of energy it receives from the Sun, no more. By any reasonable expectation, two planets so similar in structure should behave similarly in this regard. They do not. Neptune glows from inside. Uranus does not. The difference between them is unexplained, and it is one of the genuinely open questions in planetary science, a place where the models do not yet fully account for what the observations show. The rocky silicate core at the center of Neptune sits under a pressure that presses matter into forms that laboratory science is only beginning to approach. The core itself is not well characterized. Models suggest it is composed of iron, nickel, and silicate minerals, similar in broad composition to the cores and mantles of the rocky inner planets, but similar in composition is not similar in condition. At 7,000 Kelvin and pressures approaching 7 megabars, even the most stable minerals are under extreme duress. The boundary between the rocky core and the base of the ice mantle is a surface that no instrument has crossed. It is not a sharp line, planetary boundaries rarely are, but a zone of transition where the fluid above and the compressed rock below mix in ways that are difficult to model precisely. That boundary, the deepest interior threshold of the planet, is estimated to lie roughly 15,000 kilometers below the cloud tops. The cloud tops themselves, the blue face visible from space, are already remote by any terrestrial measure. 15,000 kilometers below them, the pressure approaches values found nowhere else in the solar system except inside the gas giants, Jupiter and Saturn, where the enormously greater mass creates interior conditions that exceed even these. Neptune's core boundary is not the most extreme environment in the solar system, but it is close, and it is one of the most inaccessible. The gas giants have been the focus of missions, of atmospheric probes, of long-duration orbiters. Neptune has had one flyby, one afternoon's worth of measurements from a spacecraft that could not slow down and stayed only long enough to take pictures before the momentum of its journey carried it away. The disk of Neptune in the outer solar system, that single cobalt blue point, growing slowly larger as any spacecraft approaches it, conceals within its familiar, painterly color an architecture of strangeness that extends downward for 15,000 kilometers through conditions increasingly unlike anything on the surface of this world or any other in ordinary human experience. The blue is methane's blue. It is a color produced by absorption, by the removal of red light from the thin supply of solar photons that makes it this far from the sun. What reaches the eye, or the camera, or the telescope is what is left after methane has taken what it needs. That blue is a remnant, an absence made visible. And below the layer that produces it, descending through thousands of kilometers of hot, pressurized, convecting fluid, through the permanent darkness where temperatures climb toward stellar surface values and pressures climb toward conditions that compress molecules beyond ordinary recognition, the core waits. The planet turns once every 16 hours or so, carrying its blue face through the dark. The cloud bands drift along the face of the atmosphere. The great winds, faster than any wind on Earth, push methane ice crystals through the cold upper air. And below all of it, in darkness, in heat, under pressures that add weight upon weight upon weight, with every kilometer of depth, the ice mantle churns, water and ammonia and methane pressed together into something that has no name drawn from ordinary experience, moving in slow convective cycles across timescales measured in millions of years, generating the planet's magnetic field, feeding the excess heat that bleeds out into space, and doing all of this in perfect, permanent, total quiet. No sound propagates through vacuum. The vibrations of the fluid mantle, and it does vibrate, as all fluid under pressure vibrates, have nowhere to go. The ocean of the planetary interior has no shore, no surface to break against, no atmosphere above it to carry its frequencies outward. It moves in silence so complete that silence is not quite the right word. It is the absence of the possibility of sound. The interior of Neptune vibrates against itself, against the pressure of the overlying miles of planet, and the information carried in that vibration stays there, locked inside, contributing to the thermal glow that the planet radiates outward as infrared light, the only signal its interior can send into the universe around it. From far away, Neptune is a point of blue, a single color produced by a single molecular process in the outermost layer of a complex and layered world. The methane that makes the blue is only a small fraction of the atmosphere, and the atmosphere is only the outermost layer of a planet, structured in concentric shells, each one deeper and hotter and more compressed than the one above. Below the blue, below the cold cloud tops, below the transition zone where the atmosphere thickens into something denser than air, the ice mantle extends for a depth that would swallow a whole Earth, filled with fluid that is neither gas nor ordinary liquid, nor ordinary solid, fluid that is hot enough to compare with stellar surfaces, compressed enough to change the behavior of molecules in ways that surface chemistry does not predict, and churning in slow convective cycles that have been running since the planet was young. The mantle ends where the rock begins. At that boundary, the temperature is around 7,000 Kelvin. The pressure is near its maximum, approaching those 6 or 7 megabars, 6 million times the atmospheric pressure on Earth's surface. The rocky core sits there at the center, bearing the weight of everything above it. It has been sitting there for 4.5 billion years, holding the planet together, sealed from light and from any observer, existing only in the mathematics that describes its effects on the planet's gravity and rotation. The core is the most certain and the least known thing about Neptune. Its presence is required by the planet's mass and density. Its composition is inferred. Its actual condition is beyond any current or near-future direct measurement. A needle of blue light in the outer solar system, 4.5 billion kilometers from its star, turning slowly in the dark, blue at the surface where methane meets thin sunlight, and all the way down through the dark and the heat and the pressure, structured, layered, ancient, and warm from within. The cloud tops glow in that thin, cold, borrowed blue, and below them, where nothing glows in visible light, where nothing is cold, where the pressure has long since made ordinary matter into something else, the interior continues as it has for billions of years, as it will for billions more, unhurried and unseen, the hidden architecture of a distant and extraordinary world. A single carbon atom is smaller than the wavelength of visible light. It has no color that the eye could detect, no sound, no temperature a hand could feel. And yet of all the atoms in the universe, it is the one that changes most completely, depending on how closely others press against it. Hold two forms of it in mind at once. The first is graphite, dark gray, soft enough to smear across paper with almost no pressure at all, its atoms arranged in wide flat sheets that slide against each other like pages in a loosely bound book. A pencil moves across a page and leaves a trail of those sheets behind, each one a single atom thick, each one releasing from the others so easily that the friction of writing is enough to separate them. The second form is diamond, clear as water, harder than any other naturally occurring substance, its atoms locked into a three-dimensional lattice of such rigid geometry that nothing short of a tremendous force can make it yield. Both are carbon, only carbon. The difference between them is entirely a matter of how the atoms are arranged and how much pressure was present when the arrangement was made. The sensory contrast is worth dwelling on. Graphite is something the fingers know, the soft smudge of a pencil tip, the slight resistance that turns to slide, the gray that transfers at a touch. Diamond has a different quality entirely. It is smooth and cold, and carries light through itself without scattering it. Run a finger across a polished diamond face, and there is almost no friction, only the slight chill of a material that pulls heat from the skin faster than most stones. Both of those textures, the soft gray smear and the hard cold clarity, emerge from exactly the same element arranged by pressure into different geometries. Carbon is the atom that answers most completely to the conditions around it. This is where the story of what may be happening inside a distant blue planet becomes, at its heart, a story about that single element and the question of which form it prefers under which conditions. Deep inside Neptune, in a region that begins thousands of kilometers below the cloud tops and extends inward toward the rocky heart of the planet, pressure builds in a way that has no equivalent in any ordinary experience. The weight of the overlying layers, the full depth of the fluid mantle, the crushing column of atmosphere above, accumulates with depth in the way that ocean pressure accumulates, except that here the numbers reach far beyond anything the ocean floor can offer. Neptune's interior presses inward with a force that eventually reaches several million times the pressure of Earth's own atmosphere at sea level. At those depths, the chemistry of every molecule present is under negotiation with the pressure around it, and many of the negotiations end in transformation. The starting material for what happens to carbon down there is a molecule that appears on the surface to be simple, methane. One carbon atom bonded to 4 hydrogen atoms is present in Neptune's outer atmosphere, and its presence there is easy to overlook. It is the molecule responsible for the planet's deep blue color, absorbing the red end of sunlight and leaving the blue to scatter back into space. At the surface, in the cold and relatively thin upper atmosphere, methane is stable. The 4 hydrogen atoms hold to the central carbon with enough bond energy to keep the molecule intact. But methane is not always a passenger in the upper atmosphere. Convective currents within the planet can carry material from the outer layers downward, deeper and deeper, into regions where both pressure and temperature rise dramatically. As methane descends into those conditions, what was stable at the surface becomes unstable at depth. The bonds that hold methane together, the links between the central carbon atom and each of its four hydrogen partners, are covalent bonds, which means the atoms share electrons between them. At the temperatures and pressures found in the outer atmosphere, this sharing is energetically favorable. The molecule prefers to remain whole, but as depth increases and the surrounding pressure and temperature climb into ranges that have no name in ordinary experience, those bonds come under stress. The surrounding environment begins to supply enough energy in the form of heat, in the form of the mechanical compression of pressure, to break the sharing apart. There is a threshold somewhere in the deep mantle where the covalent bonds of methane become energetically unstable. The temperature is several thousand Kelvin. The pressure exceeds roughly 1,000,000 times Earth's surface atmosphere. At those conditions, the molecule that was whole at the surface is no longer stable. The hydrogen atoms are freed. They disperse into the surrounding fluid, mingling with the broader sea of hot compressed material. And the carbon atom, stripped of its hydrogen partners, is briefly alone and reactive, floating in a medium where it must find a new arrangement or remain adrift. That reactive carbon does not stay adrift for long. Under the immense pressure of the deep mantle, the carbon atom's options for reorganization are governed entirely by thermodynamics, the set of physical laws that determine, given a temperature and a pressure, which structural arrangement of atoms releases the least energy and therefore represents the most stable state. At low pressures and moderate temperatures, the thermodynamically favored form of carbon is graphite. Those layered sheets that slide against each other, held together within each layer by strong bonds, and between layers only by weak electrical attraction. Graphite is what carbon settles into when it is at rest under ordinary conditions. But thermodynamics is not fixed. The territory of stability shifts as pressure and temperature change, and the map of which carbon form is most stable, at which conditions can be drawn with some precision. The region of this map that belongs to graphite is broad and includes nearly all conditions found on the surface of a planet like Earth. The region that belongs to diamond is different. It requires high pressure, sustained over time, to make diamond the preferred form rather than the unstable one. At pressures and temperatures representative of the deep interior of an ice giant planet, the map shifts decisively. The territory crosses a boundary. Carbon, under those conditions, does not prefer graphite. It prefers diamond. This region, this part of the pressure-temperature map, where diamond is the form that carbon settles toward, is called the diamond stability field. The name is neutral and precise. It describes a thermodynamic reality. At pressures and temperatures within this field, free carbon atoms will tend to organize themselves into diamond's tetrahedral lattice, because that lattice represents a lower energy state than any alternative. Diamond is not forced into existence here by some external agent. It is simply what carbon becomes when pressure makes it the easiest option. On Earth, the diamond stability field exists at depth. Natural diamonds form roughly 150 kilometers or more below the surface, where the pressure of overlying rock is sufficient to push carbon into the high-pressure form. The diamonds found in mines and jewelers' cases were made down there, in the slow dark of the continental crust's lower reaches, and came upward only because rare volcanic events carried them quickly, before the reduced pressure of the surface could transform them back into places where erosion eventually exposed them. The conditions that made them are entirely ordinary, the same element, the same chemistry, the same thermodynamic logic, just played out at depth. What changes on Neptune is the scale of that depth. The pressure conditions of Neptune's deep mantle, the region where methane-sourced carbon would find itself after the molecule dissociates, fall within or near the diamond stability field at pressures far beyond anything Earth's interior produces in its diamond-forming regions. The fluid that surrounds the freed carbon atoms is hot and compressed in ways that have no equivalent in the geology of a rocky planet. But the thermodynamic logic is the same. The map is the same. The boundary between graphite-favored and diamond-favored conditions is the same line drawn across the same phase diagram, operating by the same physics. On Neptune, that line is simply located at a depth where a vast quantity of carbon-bearing material resides. The phase diagram itself, that abstract map of carbon's preferred forms, is worth holding in mind as a quiet image rather than a technical document. Picture it as a landscape viewed from above, wide and flat, with two large territories separated by a border. One territory is labeled for graphite, and it covers the region of low pressure and moderate temperature conditions that include most of what life on Earth's surface ever experiences. The other territory is labeled for diamond, and it begins where pressure climbs past a certain threshold and extends across the high-pressure region of the map. The border between them is not perfectly straight, and it shifts slightly with temperature, bending in ways that careful experiments have measured over many decades. Where a carbon atom sits on that map determines what it will become or remain. At the cloud tops of Neptune, methane molecules sit well within the graphite territory, except that at those temperatures, neither diamond nor graphite forms readily, and the molecule stays intact and whole. As depth and pressure increase, the molecule descends on the map toward the border region and eventually crosses it. The carbon, once freed by dissociation, finds itself in diamond territory. The thermodynamic pressure to crystallize is real. The direction of change is set by the same laws that govern every phase transition: water freezing, salt crystallizing from a saturated solution, the slow settling of mineral grains from a cooling magma. The physics is familiar, even if the conditions are not. The question of how carbon first begins to crystallize in those conditions, how individual atoms start building the lattice that will become a diamond, involves a process called nucleation. This is the moment when a small cluster of atoms first arranges itself into the diamond structure, a cluster just large enough to be stable against the thermal agitation of its surroundings. Below a certain size, a crystalline cluster is more likely to dissolve back into the fluid than to grow. Above that size, it is energetically favorable to continue adding atoms from the surrounding medium, and the crystal grows. The threshold between these two outcomes is determined by the interplay of surface energy and bulk energy in the crystalline cluster, a balance that shifts in favor of continued growth once enough atoms have committed to the structure to make the surface cost worthwhile. In the hot, compressed fluid of Neptune's deep mantle, carbon atoms freed from their hydrogen partners are present in sufficient concentration and under sufficient pressure that nucleation, the formation of those first stable crystalline clusters, is thermodynamically plausible. Once a nucleus forms and exceeds the critical size, it begins to grow. It incorporates additional carbon atoms from the surrounding fluid. The crystal expands, atom by atom, in the permanent darkness and extreme pressure of a planetary interior that has never been visited and may never be. The physical scale of this process, imagined honestly, is quiet. There is no heat or light accompanying the crystallization in any obvious sense, no flame, no glow, no visible change in the surrounding fluid. The transformation is molecular. A carbon atom drifts through the fluid in a state of chemical freedom. It encounters the surface of a growing crystal, and because the thermodynamic conditions favor addition rather than departure, it bonds into the lattice. The crystal is larger by one atom. This happens again and again and again in the dark and under pressure at a pace set by the diffusion of atoms through a hot and viscous medium. The result, accumulated over geological time, might be a crystal of significant size, though how large diamonds can grow in Neptune's mantle remains an open question, dependent on assumptions about the density of free carbon, the viscosity of the surrounding fluid, the rate of nucleation relative to the rate of growth, and the length of time any given crystal spends in the stability field before conditions change. The best current picture suggests that diamonds might grow large enough to begin sinking, which introduces a separate and equally strange physical consequence of their formation. Diamond is dense. A cubic centimeter of diamond has a mass of roughly 3.5 grams. The surrounding mantle fluid, under the pressures and temperatures of Neptune's deep interior, is itself dense by any ordinary measure, but current estimates suggest that diamond is denser still, and density in a gravitational field determines which way things move. A diamond crystal suspended in a fluid less dense than itself will sink in the same way that a stone sinks in water, not because the stone wishes to descend, but because the buoyant force of the fluid is insufficient to support it, and gravity draws it downward. In Neptune's mantle, the direction downward leads toward the planet's rocky core. The descent would be slow. The fluid is not water, it is a hot, dense, pressurized medium with a viscosity that has no simple analogy at Earth's surface. A diamond crystal sinking through it would not fall freely. It would move with geological patience, a pace measured not in seconds or minutes, but in the longer rhythms of a planet's internal evolution. And yet it would move. The direction is set by physics and does not require any particular speed to be real. Across millions of years, across the full span of Neptune's interior history, a slow and steady drift of dense crystalline carbon toward the core is a physically coherent picture. The phase diagram alone does not guarantee this. It says only that diamond is thermodynamically favored in a certain region of pressure and temperature. The question of whether diamonds then move and where they go requires knowing the density, the viscosity of the surrounding fluid, the size that crystals achieve before sinking begins, and the internal dynamics of a planetary mantle that remains almost entirely inaccessible to direct measurement. Each of those quantities carries real uncertainty. The best current picture is a composite of experimental results, theoretical models, and analogy with better studied planetary interiors, assembled carefully into something that is plausible without being certain. There is a deeper quality to the phase diagram worth sitting with before leaving it behind. The border between graphite's territory and diamond's territory is not a wall that carbon atoms crash against. It is a thermodynamic preference, a shift in which arrangement is more stable, expressed across a continuous range of conditions. Very close to the boundary, the difference in stability between graphite and diamond is small. Far into diamond territory, the preference is strong. The same is true on the graphite side. The line itself is the region of most equal competition, where small changes in pressure or temperature tip the balance one way or the other. In Neptune's deep mantle, the conditions are estimated to fall well within diamond territory, not hovering near the boundary, but sitting in the region where diamond is strongly preferred. This is not a marginal case. The pressures and temperatures involved push carbon decisively toward the high-pressure crystalline form. The thermodynamic signal, if current models of Neptune's interior are approximately correct, is not ambiguous in direction. What remains uncertain is the rate, how fast diamonds nucleate, how quickly they grow, how efficiently they descend, and whether the conditions in the real mantle, which is not a uniform fluid, but a complex and poorly characterized mixture of water, ammonia, and methane under extreme compression, allow the process to proceed at all. The pure thermodynamics says which form carbon prefers. The actual chemistry of a mixed hot, pressurized planetary mantle is a far more complicated environment, and the fine details of how carbon behaves within it are still being worked out. But the thermodynamics is the foundation. Without the phase diagram, without the clear and well-established fact that carbon has a stability field for diamond that is simply a feature of that element's behavior under pressure, the rest of the picture collapses. The phase diagram is not a hypothesis. It is a measured, reproducible physical reality confirmed by decades of laboratory work on Earth. What is a hypothesis is the application of that reality to Neptune's interior, the inference that conditions inside the planet fall within the relevant region of the map, and that carbon is present in sufficient quantities to produce diamonds in geologically meaningful amounts. That inference rests on several things. It rests on spectroscopic measurements of Neptune's atmosphere that reveal the presence of methane. And it rests on models of how atmospheric composition changes with depth inside ice giant planets, derived from thermodynamic calculations and constrained by the planet's measured density and gravitational field. It rests on experimental work done in laboratories where extreme pressures and temperatures have been achieved, and the behavior of carbon-bearing materials directly observed, and it rests on the internal consistency of the physical picture, the way the chemistry of methane dissociation, the thermodynamics of carbon's phase diagram, and the density difference between diamond and the surrounding fluid all fit together into a single coherent sequence of cause and consequence. Each step in that sequence follows from physical law. The atmosphere carries methane. Methane descends. Pressure and temperature rise. The bonds in methane become unstable. Hydrogen disperses. Carbon is freed. The phase diagram maps the freed carbon into diamond territory. Nucleation occurs. Crystals grow. Dense crystals sink. This is not a chain built from speculation at every link. Most of the links are well-established chemistry and physics applied to estimated interior conditions. The uncertainty lives in those estimates and how precisely we know the pressure, temperature, and composition of Neptune's deep mantle, not in the physics itself. A phase diagram for carbon, drawn on a quiet page, maps with precision the conditions under which each arrangement of carbon atoms is most stable. The wide graphite territory at the lower left, the diamond field at the upper right and across the higher pressures, and between them, the boundary that separates one stable form from the other. That boundary is not an abstraction. It has been measured. It has been crossed experimentally in both directions, using real samples and real pressure systems, confirming that the transition occurs where the theory predicts it should occur. The boundary on that map is drawn in the same ink, whether it appears in a research paper or in the invisible pressure field of a planet 4.5 billion kilometers from the Sun. That is the quietest and most important thing about carbon's phase diagram. It is not a description that applies only in laboratories or only in carefully controlled conditions. It is a description of how carbon atoms behave under pressure, everywhere and always, because it describes physics rather than circumstances. Carbon atom inside Neptune's mantle does not know it is inside Neptune. It does not know it is far from Earth, far from any instrument, in permanent darkness under a pressure that no human-built container has ever sustained. It only knows the pressure and temperature around it, and it responds to those conditions according to the same thermodynamic rules that govern every carbon atom anywhere. When that the conditions are right, if the pressure is high enough, the temperature in the appropriate range, the carbon freed from its molecular partners, then diamond is simply what carbon becomes. Not remarkably, not against the odds, just quietly in the dark, because that is what the phase diagram says happens there. The softness of graphite and the hardness of diamond are not opposites in any meaningful sense. They are the same element at two different addresses on a pressure-temperature map, and the distance between those addresses is only a matter of how much weight presses down from above. On a planet with enough interior weight, enough depth, enough pressure accumulated over billions of years, the address shifts to the one labeled diamond. The element is unchanged. The arrangement is everything. This is the chemistry that underlies whatever is happening in the deep interior of Neptune right now, in this moment, in the absolute darkness below the cloud tops that glow their steady blue against the dark of the outer solar system. The methane is there in the fluid. The pressure is there, climbing with depth. The phase diagram is there, not drawn on any paper that exists inside the planet, but present nonetheless as a physical reality governing the behavior of every carbon atom the mantle contains. Where those conditions are met, carbon has a preference. It has had that preference since long before Neptune formed. The preference is built into the quantum mechanical properties of the carbon atom itself, into the particular way its electrons form bonds, into the geometry that emerges under compression. No one put it there. No process installed it. It is simply the nature of carbon, expressed most clearly and most completely under the enormous pressures that only a planetary interior can provide. The phase diagram, if held in mind as a landscape rather than a chart, becomes something else, a quiet map of inevitability, not fate in any human sense, but the thermodynamic certainty that carbon, given sufficient pressure and appropriate temperature, and the freedom that comes after the dissociation of its molecular bonds, will settle toward diamond the way a stone settles toward the bottom of still water, not hurrying, not choosing, simply following the lowest energy path available under the conditions that surround it. That path leads somewhere far below the visible surface of a blue and distant world to a crystal growing in the dark, one atom at a time, in a pressure field that will never relent, in a silence deeper than any silence on Earth. The diamond stability field is not a place that can be visited, but it is a real place, defined precisely by pressure and temperature, confirmed by experiment, and located according to the best current models of Neptune's interior, somewhere in the several thousand kilometers of hot compressed fluid that lie between that planet's cloud tops and its rocky heart. Within that field, carbon prefers a particular arrangement. Within that field, the geometry of diamond is not exceptional. It is simply the equilibrium state, the quiet answer that thermodynamics returns, again and again, when asked what carbon wants to be under these conditions. And the conditions in Neptune's deep mantle are almost certainly met. Not everywhere in the mantle, and not for all the carbon present. Methane transport from the surface to the deep interior is itself a complex and poorly constrained process, and not every carbon atom released from a methane molecule will necessarily encounter the precise conditions needed for nucleation and growth. But across a planetary interior of that scale, with a history stretching across 4.5 billion years, even a small rate of diamond formation and accumulation represents an enormous quantity of crystalline carbon, slowly and silently gathering in the dark. The transition from methane to diamond, From a simple atmospheric gas at the outer edge of the planet to a dense crystalline solid deep within it is not a sudden event. It is a sequence of slow transformations, each one triggered by depth and pressure, each one following inevitably from the one before. The methane descends into conditions where it cannot remain whole. The carbon is freed. The freed carbon enters the stability field. The stability field governs the formation of the crystal. The crystal, once formed, is subject to gravity. Gravity, combined with density, determines where the crystal goes. The sequence is long. Each step is separated from the next by the vast scale of a planetary interior and by the slow pace of geological time. But the physics connecting each step to the next is continuous and unbroken. The same laws that govern the pressure in a diamond anvil cell on a laboratory bench govern the pressure inside Neptune's mantle. The same thermodynamics that defines the boundary between graphite and diamond in a measured phase diagram defines the behavior of carbon in a fluid that no instrument has ever directly sampled. The carbon atom that began as part of a methane molecule in the cold upper atmosphere of a planet 4.5 billion kilometers from the Sun arrives, eventually, at a structural arrangement that is harder than any natural substance on Earth, and colder in a certain sense, not in temperature, which is thousands of Kelvin, but in the quiet finality of its crystalline order, locked, rigid, settled. That is what the phase diagram promises to every carbon atom that crosses its boundary into the field marked diamond. Not a drama, not a spectacle, just a settling into the most stable form available under the conditions that surround it, the way any system moves toward its lowest energy state when given the opportunity and the time. And in Neptune's interior, the time is vast, and the opportunity is real, and the conditions are, by every reasonable estimate, exactly what the phase diagram requires. Carbon, in the deep mantle of that blue and distant planet, is most likely where the map says it should be, on the diamond side of the line, arranging itself with no hurry and no witness into the rigid geometry of the hardest material the universe routinely produces from ordinary atoms under ordinary physics applied at extraordinary scale. The phase diagram is not remarkable. The conditions inside Neptune are not impossible. The chemistry is not exotic in any fundamental way. What it is instead is the quiet operation of universal physical law in a place that happens to be far away, a place where graphite softens into memory, and the same carbon, under the same rules, becomes something else entirely, simply because the pressure above it is at last enough. In the winter of 1981, a researcher named Marvin Ross sat with a set of equations and a problem that no instrument on Earth could yet resolve. The problem was this: inside the great dark bodies of the outer solar system, where pressure compounds upon pressure for thousands of kilometers in every direction, what happens to a molecule of methane? Not at the surface, where methane drifts as a cold gas in blue-tinted clouds. Deep inside, where the weight of a planet bears down from every direction and the ordinary rules of molecular chemistry begin to give way. Ross worked through the pressure-temperature conditions that theorists had estimated for the mantles of Uranus and Neptune, applied what was then known about hydrocarbon behavior at extreme states, and arrived at a conclusion that his instruments could not confirm. Carbon, he calculated, would separate from its hydrogen partners. It would become free, and under the pressures estimated to exist inside those distant worlds, free carbon would not drift or dissolve or disperse. It would crystallize. It would become diamond. The calculation sat in the literature, the way early calculations often do, acknowledged, cited, held in a kind of respectful suspension, while the tools needed to test it remained a generation away. Ross had identified the shape of something real, but the shape was drawn in theory alone, and theory without experiment is a kind of patient waiting. The idea waited. The instruments that would eventually speak to it were not yet built. The lasers were not yet powerful enough, the X-ray sources not yet bright enough, the understanding of hydrocarbon behavior under shock compression not yet precise enough to reach the conditions his equations described. So the hypothesis rested, neither confirmed nor dismissed, while the planet it described continued its slow orbit in the cold dark beyond the reach of any probe yet sent to measure it. What Ross had proposed in the language of the science was a sequence of events beginning with dissociation and ending with crystallization. Methane carried downward by the convective mixing of Neptune's interior would encounter pressures and temperatures far beyond anything the molecule could sustain in its ordinary form. The 4 hydrogen atoms bonded to each carbon center would be pulled away. The bonds themselves, strong as they are under ordinary chemistry, would become energetically unstable at the conditions that exist several thousand kilometers below Neptune's cloud tops, where pressures rise into the millions of Earth atmospheres and temperatures climb into the thousands of Kelvin. Hydrogen, once freed from those broken bonds, would disperse into the surrounding fluid, a dense, hot, compressed medium that is itself neither gas nor liquid in any familiar sense. And the carbon atoms, reactive and momentarily unattached, would be left in an environment where the thermodynamics strongly favored one particular arrangement of their electrons and bonds. They would find each other, they would organize, they would form the rigid tetrahedral lattice that at those pressures is simply what carbon prefers to be. The word diamond carries weight in ordinary language that is worth setting aside for a moment. In the common imagination, it carries associations of rarity, of surface and light, of a gem held up to catch sunlight and scatter it into color. The diamond that Ross's calculations pointed toward had nothing to do with any of that. It would form in complete darkness at depths where no light from the sun above had ever penetrated, under pressures that would compress and distort almost any other material beyond recognition. It would form not as a jewel, but as a crystalline solid with a particular geometric arrangement of carbon atoms, the same arrangement that gives surface-found diamonds their hardness and their optical properties, but occurring here not by rarity or geological accident, but as the natural chemical outcome of the conditions present throughout a broad region of Neptune's interior. Not a wonder, a consequence. The hypothesis rested on something geometrically elegant about the interior of Neptune. The planet's mantle occupies a vast region, stretching from several thousand kilometers below the cloud tops down toward the boundary with the rocky core deep inside. Across that region, pressure and temperature rise steadily with depth, following a gradient that passes through the thermodynamic territory where carbon stability strongly favors the diamond phase. If methane is present throughout the upper portion of that region, and if it dissociates under the conditions present there, then the carbon it releases does not encounter those conditions at a single point. It encounters them across thousands of kilometers of planetary depth. The diamond-forming zone, if it exists, is not a narrow layer. It is a broad region of a planet. And within that region, the process would not be an event, but a condition, something happening continuously, steadily, invisibly, as long as the planet's interior maintains the temperatures and pressures that make it possible. The word rain in the hypothesis is a metaphor that requires careful handling. Rain on Earth is a rapid thing, visible, audible, felt on skin, over in hours. The falling Ross's hypothesis described would be nothing like that. Diamond, once it crystallizes in Neptune's fluid mantle, is significantly denser than the surrounding medium. A cubic centimeter of diamond weighs roughly 3.5 grams. The fluid around it, hot and pressurized as it is less dense than that. The result is a gravitational imbalance. The crystal would sink, not quickly, not in any way that bears comparison to water falling through air. The mantle fluid is dense and resistant, and the scale of the distance to be covered is thousands of kilometers. The sinking would be slow by any measure the body can feel, a geological process, measured not in seconds or hours, but in the long rhythms of planetary time. Crystal after crystal, over the vast span of Neptune's lifetime, drifting downward in the permanent dark. In aggregate, across the whole interior of the planet and across billions of years, the process would amount to something continuous and immense. Individually, each crystal's descent would be imperceptible, a slow, silent movement through a medium that offers no surface to land on, no moment of impact, only a gradual approach to the boundary between fluid mantle and rocky core somewhere in the deep center of the world. That boundary, the surface of the rocky core, if surface is even the right word for something buried beneath 6 or 7 million Earth atmospheres of overlying material, would receive, in this picture, a slow and continuous accumulation, diamond falling from above, diamond settling, a layer growing over geological time, not in the way sediment builds on an ocean floor, but in the way that any material denser than its surroundings must eventually come to rest at the lowest available point in the gravity well it inhabits. The core of Neptune, in this picture, would be rimmed by a growing shell of compressed carbon, not a thin film. Over the lifetime of the planet, 4.5 billion years, the accumulated mass might be substantial. The numbers are uncertain, and the uncertainties are wide, but the logic of the process, once the initial dissociation and crystallization are granted, leads here by simple gravitational consequence. For 2 decades after Ross's paper, the hypothesis existed in this state of logical plausibility without experimental grounding. The conditions he described, pressures above 1 million atmospheres, temperatures of several thousand Kelvin, were at the outer edge of what laboratory systems of the era could achieve, and the techniques for observing what happened to materials under those conditions in real time had not yet reached the precision needed. There were theoretical refinements, revisions to the estimated pressure-temperature profile of Neptune's interior as models improved, debates about the composition of the mantle fluid and what it meant for carbon chemistry. The picture was adjusted and re-examined, but the core question, does carbon actually crystallize into diamond under these conditions, or does it do something else, remained unanswered by measurement. The difficulty was not only one of pressure, it was also one of time. A shock compression experiment can achieve enormous pressures and temperatures for a very short duration, billionths of a second, and the question was whether crystallization, which requires atoms to rearrange themselves into an ordered structure, could happen fast enough to be captured in that window. Crystal growth often requires time. Whether diamond nucleation, the first moment when a few carbon atoms arrange themselves into the embryonic form of a crystal lattice, could occur on the timescale accessible to a laser shock experiment, was itself an open question. The answer would depend on how strongly thermodynamics favored the diamond phase at those conditions, and on the kinetics of the nucleation process, which are notoriously difficult to predict from theory alone. What changed the situation was not a single breakthrough, but a convergence of capabilities, more powerful laser systems, more brilliant X-ray sources, and new methods of using those X-rays to detect crystal structure in a material during the brief window of a shock event. By the early decades of the current century, the tools had arrived that Ross's calculation had been waiting for. Researchers working with hydrocarbon materials subjected them to pressures and temperatures in the range his equations had identified, and they watched with X-ray pulses for the signature of crystalline structure forming in real time. The result, reported in 2017, was a diffraction pattern, a set of rings on a detector screen produced by X-rays scattering off a regular crystal lattice that corresponded to diamond, not graphite, not an amorphous carbon material. Diamond, forming in a hydrocarbon sample under shock compression at pressures and temperatures estimated to fall within Neptune's mantle range. The material used in that experiment was not methane, and that detail matters for understanding what the result does and does not establish. Polystyrene, a common hydrocarbon material whose carbon-to-hydrogen ratio is broadly similar to the mixture expected in Neptune's interior, though not identical, was used as the sample. The choice was practical. Pure methane, at the densities and pressures involved, is difficult to prepare and confine, while polystyrene can be formed into precise thin sheets and loaded into the experimental apparatus with high repeatability. The use of a proxy material introduced uncertainties about exactly how the results translate to real planetary conditions. Researchers acknowledged those uncertainties. The experiment was not a direct simulation of Neptune's mantle. It was a demonstration that hydrocarbon materials, under conditions in the same pressure-temperature neighborhood as those in Neptune's interior, produce diamonds spontaneously and on the timescale accessible to a shock experiment. That demonstration was, itself, a significant step, the first direct observational evidence that the process Ross had calculated in 1981 could actually occur. The step from laboratory demonstration to planetary process is not a straight line, and the researchers who reported the result were careful about this. They were measuring what happens to polystyrene under specific shock conditions lasting nanoseconds. Neptune's interior is a complex, dynamic system operating over billions of years with a mantle composition that differs from polystyrene in ways that may be significant. The presence of water, ammonia, and other compounds alongside the hydrocarbons and a pressure-temperature gradient that evolves slowly with depth rather than being imposed instantaneously by a shock wave. Whether the nucleation of diamond observed in the laboratory translates to continuous diamond formation in a real planetary interior depends on many factors that the experiment did not and could not address. The experiment opened a door, it did not walk through it. Beyond the question of whether diamond forms, there is the separate question of what happens to it once it does. Crystal growth, in the laboratory setting of a shock experiment, terminates when the shock dissipates, leaving small diamond crystallites. The researchers estimated sizes in the nanometer range from the broadened diffraction peaks they observed. In Neptune's interior, the conditions that favor diamond would persist for as long as the planet's internal heat keeps temperatures and pressures in the relevant range. A diamond crystal that nucleates in Neptune's mantle would not be terminated by a dissipating shock. It would sit in an environment that continues to favor its existence. It would grow, slowly, as additional carbon atoms from the surrounding dissociated methane found the crystal surface and joined the lattice. The size it could ultimately reach is unknown and depends on conditions, the local concentration of free carbon, the temperature, the viscosity of the surrounding fluid, the rate at which convection moves material through the crystallization zone. But there is nothing in the physics that prevents the crystals from growing far beyond the nanometer scale of the laboratory specimens. The slow descent of those growing crystals through Neptune's mantle carries an energy implication that connects the interior chemistry of the planet to something measurable from outside it. When a dense object sinks through a fluid under gravity, the gravitational potential energy it loses does not disappear. It converts to heat, partly in the friction between the sinking object and the surrounding medium, and partly in the work done by the sinking object, compressing the fluid below it. In a planetary interior, where the sinking material is not a single object, but a distributed continuous rain of crystals falling through thousands of kilometers of mantle, that energy release is spread over an enormous volume and an enormous time. The thermal contribution of any single crystal is negligible. The thermal contribution of the process operating continuously across the full mantle volume of a planet over geological time is not. Neptune radiates into space roughly 2.5 times more energy than it receives from the Sun. This ratio, the planet's internal heat excess, has been measured from outside the planet and is well established. It is a real and significant number. Something inside Neptune is generating heat and has been generating it for a very long time at a rate that cannot be explained by the slow cooling of the planet's initial formation heat alone, at least not under the simplest models of planetary cooling. Something additional is happening. Several mechanisms have been proposed, and none has been definitively established as the primary cause. One of those proposed mechanisms is the gravitational energy released by the sinking of dense material, including, potentially, diamond, through the mantle fluid. What makes this particular connection between the interior chemistry and the measurable external heat emission significant is that it represents a possible observational handle on a process that is otherwise completely inaccessible. No instrument can peer into Neptune's mantle. No probe has descended through its cloud tops, and even if one had, the depths at which diamond formation would occur are far below any achievable entry depth. The mantle chemistry of Neptune is, in practice, forever beyond direct observation. But if the gravitational settling of diamonds contributes to Neptune's internal heat, then the heat itself, detectable from a spacecraft or even from ground-based infrared telescopes, carries embedded within it some information about the interior process. The connection is indirect and mediated by many other factors, and the calculation of exactly how much heat diamond settling would contribute is uncertain. But the possibility of a physical link between a deep interior process and an externally measurable quantity is exactly the kind of thread that planetary science attempts to trace. Uranus complicates the picture, as Uranus tends to do. In size and bulk composition, Uranus and Neptune are near twins, similar radius, similar mass, similar estimated proportions of hydrogen, helium, and heavier compounds. The same basic interior models that predict diamond rain for Neptune apply, with adjustments to Uranus, and yet Uranus does not show the same internal heat excess. Uranus radiates almost exactly the energy it receives from the Sun, no more. Whatever process is releasing heat inside Neptune does not appear to be operating at the same rate inside Uranus, or is suppressed in Uranus by some other mechanism that prevents the heat from reaching the surface. This discrepancy between two apparently similar planets is one of the genuine open puzzles of ice giant science, and the diamond rain hypothesis, taken alone, does not resolve it. If diamond settling is contributing to Neptune's heat, why is it not contributing equally to Uranus's heat? Are the interior conditions of the two planets more different than their bulk properties suggest? Does Uranus have a stable stratified interior that suppresses the convection needed to carry carbon into the diamond-forming zone? Is there a layer in Uranus's interior that traps heat below a certain depth, preventing it from escaping even if it is being generated? None of these questions have settled answers. They are live problems in planetary science, and the diamond rain hypothesis sits inside them rather than above them, a plausible piece of a larger puzzle whose full picture has not yet come into focus. The hypothesis contributes a possible explanation for one observed anomaly, while leaving another anomaly, equally significant, still unexplained. This is the ordinary condition of science when it works on problems it cannot yet directly measure. The picture is partly clear and partly not. The parts that are not clear are named plainly, and the investigation continues. What the 2017 experiment established, and what subsequent work with more compositionally accurate analogs has continued to support, is that the chemistry at the heart of the diamond rain hypothesis is real. Carbon-bearing materials, subjected to the pressure and temperature conditions estimated for Neptune's mantle, do produce diamond. They produce it quickly, under the brief conditions of a shock experiment. The inference to a planetary process that the same chemistry operates continuously and at scale inside Neptune requires additional assumptions and carries real uncertainties, but it rests on a foundation that did not exist before that experiment. Ross's 1981 calculation, which had waited patiently through decades of instrumental development, finally had a laboratory echo, not a confirmation of the full planetary hypothesis, but a confirmation of its chemical core. The image the hypothesis presents, not as a proven fact, but as the best current picture of what may be happening inside Neptune, is one of quiet, distributed geological process. Not a storm, not a dramatic event, something more like the slow accumulation of sediment on a deep ocean floor, except that it is happening in complete darkness, under pressures that have no analog anywhere in the natural world, accessible to human experience, at temperatures that would vaporize any ordinary material, and it has been happening for billions of years. The crystals that may have settled to the core boundary over Neptune's lifetime have been there since long before Earth's oceans formed. They formed in a darkness that has never been interrupted, descended through a fluid that no chemistry has ever stirred from outside, and came to rest at a depth where the pressure is beyond the reach of any laboratory instrument yet built. The falling itself, imagined as a kind of slow planetary weather, invisible and interior, has a quality of patience that mirrors something in the physical character of the outer solar system. Everything out there is slow. Neptune takes 165 Earth years to complete a single orbit. Its seasons, such as they are, last for decades. The timescales on which its interior operates are longer still. What happens inside Neptune does not happen on human time. It happens on the time of planets, which is to say, on a time so long and so steady that the concept of waiting becomes meaningless. The diamonds, if they are falling, have always been falling. They will be falling long after every instrument built to look for evidence of them has gone dark and cold. There is something in this picture, in the patience of it, the scale of it, the silence of it, that the hypothesis wears well, regardless of whether it is ultimately confirmed. The science underneath it is real. The chemistry of carbon under pressure is not in doubt. The dissociation of hydrocarbons at high pressure and temperature has been observed. The formation of diamond in shocked hydrocarbon samples has been demonstrated. The density contrast between diamond and the estimated mantle fluid is real. The gravitational consequence of that density contrast, that denser material sinks, is as fundamental as gravity itself. Each step in the chain, from methane to falling crystal, rests on ground that is either well established or experimentally supported. What remains uncertain is the integration of those steps into a complete, working, real planetary interior with all the complexity that a real planetary interior contains. That uncertainty is, in this case, genuinely restful rather than troubling. It does not indicate that the science is shaky. It indicates that Neptune is far away and that its interior is behind barriers of pressure and distance that current technology cannot cross. The problem is not a failure of understanding, but a practical limit on observation. The hypothesis stands not in the dark, but at the edge of the light that current instruments can cast, partially illuminated, well reasoned, with its foundation in place and its upper floors still being built. There is a quality to the heat Neptune releases into space, that quiet excess, 2.5 times what the sun provides, bleeding gently outward in the infrared, that takes on a different texture in the context of the diamond rain hypothesis. Infrared light is not visible. It does not produce color or brightness in the way that ordinary light does. A spacecraft or ground-based telescope equipped to measure it detects it as a set of values in a data stream, numbers representing energy flux at specific wavelengths. Neptune, measured this way, glows, not with reflected sunlight, which is also there, but is accounted for separately, with its own warmth. The planet is radiating from within, steadily, in all directions, into the cold of the outer solar system, where the background temperature of space is barely above absolute zero. That warmth has a source, or multiple sources, that the science has not yet fully resolved. It may be the remnant heat of Neptune's formation, still slowly escaping after 4.5 billion years. It may reflect active processes in the interior, convection, phase transitions, chemical reactions, the settling of dense material. It may be some combination of these that no single explanation adequately captures. What the diamond rain hypothesis proposes is that one thread in that complex warmth, one contribution to that steady infrared glow, may carry, in thermodynamic form, the energy released by crystals sinking slowly through thousands of kilometers of pressurized fluid, not all of the warmth, not necessarily a dominant contribution, but a real one, if the hypothesis is correct. Standing at the boundary of that question, what fraction of Neptune's excess heat might be attributable to the gravitational settling of diamond? The science is honest about the limits of what it knows. The models are imprecise at this level of detail. The composition of the mantle fluid is not known with certainty. The rate of diamond production depends on variables that cannot yet be measured. The thermal history of the planet involves processes that are difficult to disentangle from each other, even with excellent theoretical tools. The question is open, and it will remain open until instruments and missions make it possible to constrain the models more tightly. What exists now is a hypothesis in which each piece is physically grounded, assembled into a picture that is coherent and testable in principle, and waiting, as Ross's calculation waited, for the tools that will allow the waiting to end. That picture Neptune as a planet whose interior may be, at this moment and at every moment, producing diamonds and releasing them to a slow gravitational fall through thousands of kilometers of pressurized dark, is not offered as a certainty. It is offered as the best current version of what may be happening inside one of the most remote and least visited bodies in the solar system. It is offered carefully, with its uncertainties named and its experimental support accurately characterized. And within those boundaries, it is a picture that the evidence, as it now stands, does not exclude. The chemistry is real, the physics is sound. The process, if it is occurring right now, steadily, silently, at a depth no human instrument has ever reached. Inside a world that most people have never seen except as a faint blue point in a photograph taken by a single spacecraft as it flew past in 1989 and continued outward into the dark. The infrared warmth of Neptune drifts outward from that blue point in all directions, thinning with distance, diluting into the cold. Some of it crosses the vast interval between Neptune and the inner solar system, an interval so wide that light takes more than 4 hours to cover it. Some of that warmth after that crossing arrives in the vicinity of instruments designed to measure it, and in the numbers those instruments record, the diamond rain hypothesis proposes that there may be a signal, faint, partial, inextricably mixed with the outputs of other interior processes, of crystals falling in the dark, 4 billion kilometers away, in the center of a world that will not be visited again for a very long time. The heat continues outward. The planet continues its slow orbit. Inside it, in the permanent and total darkness of its compressed mantle, the conditions that existed when Ross wrote his equations in 1981 continue to exist, unchanged by the decades of theoretical work and laboratory measurement that have accumulated around the hypothesis they gave rise to. Whether diamond is falling there or not, the pressure is real, the temperature is real, the methane is real, the carbon atoms that methane carries into that environment are real, and the question of what those carbon atoms do, when the bonds that hold them in their molecular forms finally give way under the weight of millions of kilometers of overlying planet, remains one of the most quietly compelling, open problems in the science of worlds beyond this one, held for now in the same patient suspension as the diamonds themselves may be, drifting slowly downward through the dark. A diamond anvil cell sits on a laboratory bench in near silence. It is smaller than a human fist. 2 gem-quality diamond tips face each other across a gap so narrow it would be invisible to the naked eye. A space measured not in millimeters, but in the width of a few stacked cells from the lining of a lung. Between those 2 polished points, a sample of matter smaller than a grain of coarse salt has been placed with instruments finer than surgical needles. The room around the device is quiet. The bench is still, and inside that invisible gap, the pressure building between the 2 diamond faces is reaching conditions that exist nowhere else on the surface of this planet. This is how scientists reach the interior of a world 4.5 billion kilometers away. Not with spacecraft. Not yet with 2 gemstones, a press, and a sample smaller than the period at the end of a sentence. The diamond anvil cell works because diamond is the hardest natural substance known. When force is applied to 2 opposing diamond tips across an area that's small, the pressure concentrates to a degree that would be impossible to achieve over a larger surface. Pressure is force divided by area, and here the area is almost nothing. The force distributed across that near nothing climbs to pressures exceeding 300 gigapascals, pressures found inside the deep mantles of the largest planets, pressures that exist in the hearts of distant worlds. The diamond itself does not crack because diamond does not yield to diamond. It holds the sample in a grip that nothing on Earth's surface in any natural setting would ever provide. What makes the device more than a simple press is that diamond is transparent to X-rays. Light passes through it. Synchrotron radiation, generated by electron beams moving at close to the speed of light in large circular accelerators, can be directed through the diamond tips and through the compressed sample inside. And the way that radiation scatters on the other side carries information about the crystal structure of whatever is being compressed. Different structures scatter differently. A disordered fluid leaves one pattern on the detector. A crystalline lattice leaves another, sharp rings, precise angles, the unmistakable geometric signature of atoms arranged in a repeating order. The instrument can hold matter under planetary pressure, and it can read what that matter is becoming without ever having to open the gap and let the pressure go. The sample inside the cell sits in a tiny chamber, often a drilled hole in a thin metal foil surrounded by a pressure medium that helps distribute the force evenly. The whole assembly, foil, chamber, sample, medium, is no larger than the cross-section of a human hair. The diamonds are polished to tolerances measured in fractions of a wavelength of light. The tips, called culettes, are ground flat to within almost nothing. The researchers who load these cells work under microscopes, using tools made from tungsten wire, moving samples that are not quite visible to the unaided eye. The precision of the loading is the precision of the experiment. One speck out of place, and the pressure does not distribute correctly, and the results cannot be trusted. At pressures above 100 gigapascals, the apparatus can generate temperatures as well, using focused laser beams directed through the diamond tips and into the sample. The laser energy heats the compressed material to thousands of Kelvin, to temperatures comparable to the outer layers of the sun, held there inside a gap smaller than a blood cell's width, between two gem-quality stones resting on a laboratory bench. The combination of extreme pressure and extreme temperature is what makes the cell capable of simulating the deep mantle of a planet like Neptune, not the bulk of it, not the full scale of it, but the thermodynamic conditions, the pressure, the temperature, the chemical environment can be reproduced at this miniature scale, and the physics that governs carbon at these conditions does not change because the sample is small. An atom under 300 gigapascals behaves the same whether it is one of 10 billion atoms in a planetary mantle or one of a few trillion atoms in a speck between two diamonds on a laboratory bench. The physics is the same. The phase behavior is the same. What the diamond anvil cell finds in that invisible gap is what Neptune holds in its deep interior. Still, the diamond anvil cell has limits. It achieves high pressure in a static, sustained way, holding the sample at elevated conditions for seconds, minutes, sometimes longer. The planetary interior is also roughly static on a human timescale, but the mantle of Neptune is dynamic in ways that the cell cannot fully replicate. The fluid is moving, the temperature varies with depth. Carbon-bearing molecules are arriving continuously from above as they are transported downward. The cell gives a fixed reading at a fixed point in pressure, temperature, space. It can map the phase diagram of carbon-1 data point at a time, accumulating knowledge slowly, building a picture of where diamond forms and where it does not. But to probe the fast, energetic conditions of a shockwave moving through a planet, conditions that may replicate the dynamic behavior of material during sudden compression events in a planetary interior, a different kind of instrument is needed. That instrument does not sit quietly on a bench. It fills a building. The National Ignition Facility at Lawrence Livermore National Laboratory in California houses the largest laser system ever built. The building that contains it is roughly the size of a sports stadium. Inside, 192 separate laser beams travel from their source through a long sequence of amplifying components, growing in energy at each stage until they converge on a single target chamber at the center of the structure. The target chamber is a sphere roughly 10 meters across, its inner surface lined with the ports of all those converging beams. The chamber walls are thick enough to contain what happens inside. At the center of the chamber, held in position by a mechanical tower, sits the target. It is smaller than a pea. When the system fires, all 192 beams arrive at that target in a pulse lasting only a few nanoseconds, a few billionths of a second. The energy delivered in that pulse can reach more than 1 megajoule of ultraviolet light, converging on something smaller than a pea from every direction at once. The effect on the target is not heating in the ordinary sense. It is ablation. The outermost layer of the target material is driven off so rapidly that the reaction pushes inward, generating a shock wave that travels through the material at enormous speed, compressing it ahead of the wavefront to pressures that can exceed those generated by the static diamond anvil cell, while simultaneously driving the temperature into a range of thousands of Kelvin. The entire event, the shock wave propagating through the material, compressing and heating it, driving it through whatever phase transitions the extreme conditions produce, happens and is over within nanoseconds. The experiment lasts less time than it takes light to cross a room. This is dynamic compression as opposed to the static compression of the diamond anvil cell. The two approaches access the same pressure-temperature territory in fundamentally different ways. The diamond anvil cell holds pressure steady and reads the equilibrium state. The laser shock system drives pressure in a fast wave and reads the material mid-transition, catching it in the act of changing. They are not competing methods. They are complementary ones. Each sees something the other cannot. In experiments conducted with high-powered laser systems like these, hydrocarbon samples have been compressed to pressures exceeding 100 gigapascals while being heated to temperatures above 5,000 Kelvin. The hydrocarbon chosen for many of these experiments is polystyrene, the same lightweight foam used in coffee cups and packaging material. At room temperature and ordinary pressure, polystyrene is a white, brittle solid that crumbles under a thumbnail. Its chemistry is built from long chains of carbon and hydrogen. When a laser shock wave drives through a polystyrene sample at planetary pressures and temperatures, those chains come apart. The carbon-hydrogen bonds dissociate under the energetic assault. Hydrogen is released into the shocked fluid. Carbon atoms, suddenly free of their hydrogen partners, find themselves in a high-pressure environment where the thermodynamics favor a particular arrangement, not a chain, not a gas, but a crystal, diamond. The evidence for this does not come from opening the sample afterward and looking for crystals. The event is over in nanoseconds, and the sample is destroyed before anything can be recovered. The evidence comes from reading what is happening inside the sample while the shock wave is still moving through it, using a different kind of light, X-ray light, delivered in a pulse precisely timed to coincide with the moment of peak compression. The X-rays pass through the compressed sample and scatter off whatever structure is present inside it. If the carbon has organized into a crystalline lattice, the scattered X-rays will resolve into the characteristic diffraction rings of diamond. If no crystal has formed, those rings will be absent. In the key experiments at SLAC, the facility in California that houses the LINAC coherent light source, X-ray pulses generated by a free electron laser were synchronized with the shock compression event. The free electron laser produces X-ray light that is extraordinarily bright and coherent, delivered in pulses on femtosecond timescales, millionths of a billionth of a second. These pulses are short enough and bright enough to capture a snapshot of the interior of a shock-compressed sample at the precise moment of peak pressure, the way a very fast camera captures the suspended instant of a splash. The X-ray pulse arrives, passes through the sample, scatters, and reaches the detector. The detector records the pattern. The pattern is red. In those experiments, the pattern that appeared on the detector was the diffraction signature of diamond, not graphite, not an amorphous carbon phase. Diamond, the specific tight tetrahedral crystal structure that forms only under conditions where diamond is thermodynamically stable. The rings appeared at the correct angles. The spacing matched the known lattice parameters of diamond. The signal was unambiguous. In a sample of polystyrene compressed to conditions broadly representative of Neptune's interior, diamond had formed. It had formed quickly within the nanoseconds of the shockwave passage, and the X-ray light had caught it in the act. This is the kind of result that accumulates slowly in science. It does not arrive as a single overturning moment. It arrives as a data point, checked against previous data points, consistent with the phase diagram that static experiments had been building for years, providing a new kind of confirmation from a new direction. The diamond anvil cell had shown that diamond is stable at these pressures. The laser shock experiments showed that diamond can nucleate and grow at these pressures on timescales fast enough to be consistent with the dynamic processes of a planetary interior. The two results together build something more durable than either one alone. Polystyrene is not Neptune. Its chemistry is a simplified analog. The carbon-to-hydrogen ratio broadly resembles a hydrocarbon-rich planetary mantle mixture, but it is not a true match to the water, ammonia, and methane fluid that makes up most of Neptune's interior. Researchers recognized this limitation from the beginning. The early experiments with polystyrene were a proof of concept, a demonstration that the method worked, that diamond formation could be detected in real time under shock compression, that the physics was tractable. Later experimental work has pushed toward greater compositional accuracy, using mixtures of water, methane, and ammonia in proportions designed to more closely resemble what the interior of an ice giant actually contains. These more compositionally faithful experiments are technically harder. The sample preparation is more complex. The behavior under shock is more difficult to predict. But the fundamental result, that carbon-bearing material, driven to Neptune-relevant pressures and temperatures, forms diamond, has held across different compositions and different experimental geometries. There is something worth sitting with in the image of polystyrene as the stand-in for a planetary interior. The material is so thoroughly ordinary, so familiar from the texture of takeout containers, from the soft crunch of packing foam, from the white beads that fall out of the sides of a cushion. Nothing in its ordinary existence suggests that it carries any relationship to the deep interior of a planet circling the sun 4.5 billion kilometers away. And yet the carbon in polystyrene obeys the same chemistry as the carbon in Neptune's mantle. Under the same pressures and temperatures, it makes the same choices. The atoms do not care what context they came from. They respond to the conditions they are in. The diamond anvil cell and the laser shock system approach the same region of pressure-temperature space from opposite directions. The diamond anvil cell enters that region slowly, stepping up pressure in increments, measuring each stable state as it goes, mapping the equilibrium landscape of carbon's phase behavior. The laser shock system enters that region in an instant, driving matter through the landscape at high speed and reading it mid-flight. Where they overlap, they agree. The diamond stability field that the phase diagram predicts, that region of pressure and temperature where diamond is what carbon becomes, appears in both. The boundary between the region where carbon stays disordered and the region where it crystallizes into diamond is marked by real data, not extrapolation. The theoretical predictions made by calculating pressure-temperature conditions from first principles align with what the experiments directly measure. This agreement between theory and experiment, built across different methods over many decades, is the foundation beneath the diamond rain hypothesis. The hypothesis does not rest on a single dramatic finding. It rests on the accumulated weight of a phase diagram built one data point at a time, each point coming from a different instrument, a different research group, a different experimental approach, all of them landing in consistent positions, outlining the same landscape, confirming the same transitions. Science accumulates this way, quietly, without announcement. Each result adds a small weight to one side of the scale, and over time the scale settles. The X-ray free electron laser at SLAC occupies a tunnel almost 2 miles long on the Stanford campus, buried beneath a flat piece of ground that gives no sign of what lies below. Electrons are accelerated to nearly the speed of light along that tunnel by a system of radio frequency cavities, each one adding a small increment of energy, the electrons moving faster and faster until they have nearly as much energy as they can hold. At the end of the tunnel, the electrons are bent by magnetic undulators, arrays of magnets whose alternating poles force the electrons to wiggle back and forth as they travel. This wiggling causes them to emit light. At these energies, the light they emit is X-ray light. And because all the electrons are moving together, forced by the undulators into synchronized oscillation, the light they emit is coherent, its waves all in phase, its pulses extraordinarily bright. But brightness is the key. Ordinary X-ray sources, even synchrotron sources, are too dim to capture the interior of a shock-compressed sample in a femtosecond. The sample exists at peak compression for only nanoseconds. The X-ray flash has to be both fast enough to catch that peak and bright enough to produce a detectable diffraction signal in the fraction of that window available for measurement. The free electron laser is fast enough. It is bright enough. It is the instrument by which it became possible to take a photograph in X-ray light of diamond forming inside a shocked hydrocarbon sample at the moment of its formation. In the experiments, the timing of the X-ray pulse relative to the shock arrival at the sample position was controlled to within a fraction of a nanosecond. The laser that drove the shock wave fired. The shock wave moved through the material. At the calculated moment of peak compression, before the wave had passed through and pressure had begun to release, the X-ray pulse arrived. The scattered pattern it produced was recorded. Then the experiment was over. The sample was gone. The data remained. The diffraction rings of diamond appeared in those data at angles corresponding precisely to the spacing of the carbon-carbon bonds in diamond's crystal lattice. The lattice spacing of diamond is known from measurements of natural and synthetic diamond going back more than a century, and the positions of its diffraction features are not ambiguous. When those features appear in data from a shocked hydrocarbon sample, they mean that diamond has formed. There is no other carbon structure that produces those rings at those angles. These results did not emerge in isolation from the rest of the experimental literature. Diamond anvil cell experiments had been mapping carbon's phase diagram for decades, gradually extending the range of accessible pressures and temperatures, gradually filling in the high-pressure, high-temperature corner of the diagram where diamond stability was predicted, but difficult to confirm directly. Static experiments at lower pressures had long confirmed that diamond is stable above roughly 50 gigapascals at room temperature, the rough boundary of the diamond stability field on the cold side of the phase diagram. At higher temperatures, the boundary shifts, and the experiments needed to track it require both high pressure and high temperature simultaneously, which is technically harder. Laser heating inside diamond anvil cells, using the same focused laser technique that heats samples in shock experiments, but applied to a statically compressed sample, extended the static data into the high temperature region. Those data and the shock data arrived at the same place from different directions. The picture they assembled together shows Neptune's interior as far as it can be estimated from internal structure models, sitting comfortably inside the diamond stability field. The pressure-temperature profile of Neptune's fluid mantle increasing from roughly 1 megabar at the outer boundary to 6 or 7 megabars near the core, with temperatures climbing from thousands to tens of thousands of Kelvin, traces a path through the phase diagram that crosses well within the region where experiments confirm that carbon crystallizes into diamond. The experiments did not just confirm that diamond can form at Neptune-relevant conditions. They confirmed it at many points along that path, at different pressures and temperatures that sample different depths in the planetary mantle. There is a practical boundary to what laboratory experiments can fully replicate. The very highest pressures in Neptune's interior, approaching the core boundary, where 7 megabars compresses whatever lies there beyond easy physical intuition, remain at or near the edge of what current instruments can achieve. The static pressure record in diamond anvil cells has climbed over recent decades, but approaching 6 or 7 megabars in a sample while also maintaining high temperatures is extraordinarily difficult, and the data in that part of the phase diagram remains sparse. Shock experiments can access those pressures, but the samples are so far outside ordinary conditions that interpreting the data requires careful theoretical modeling of the equation of state, how the material's volume, pressure, and temperature relate to each other under shock. The deep core boundary of Neptune remains in a zone where the experimental coverage is real, but not complete. The incompleteness is not a failure, it is the current frontier. Every year that diamond anvil cells achieve higher pressures, every year that shock experiments refine their diagnostic methods, and every year that theoretical calculations from first principles extend their reach into the multi-megabar regime, each year narrows the zone of genuine uncertainty. The picture of what happens to carbon at Neptune-relevant conditions is not finished, but it is not vague. It has edges. They are real edges, defined by real experiments, and they are moving. Outside the laboratory building, on a clear night, the air is still. Far above, in the dark between the visible stars, Neptune is an invisible point, too faint to see without a telescope, drifting in an orbit that takes it 165 years to complete. Its blue disk, if a telescope were turned toward it, would show nothing of what lies beneath. The cloud tops glow in methane-colored blue. Below them, in the dark, the mantle extends for thousands of kilometers of pressurized fluid in permanent night. And somewhere in that fluid, carbon is reaching conditions where the experiments say diamond forms. Whether it actually rains, whether diamond crystals nucleate, grow large enough to survive as discrete particles, and sink through the mantle fluid under their own density, remains a hypothesis rather than a confirmed observation. The experiments confirm the formation of diamond under relevant conditions. They do not confirm the full dynamics of what happens after formation, how large the crystals grow, how quickly they sink, how the sinking is influenced by the viscosity and density structure of the surrounding fluid. These questions require either computational modeling, detailed enough to capture the behavior of matter at planetary scale, or direct measurements from within Neptune itself, measurements no instrument has yet made. What the experiments provide is the thermodynamic case. The formation step is confirmed. Carbon-bearing material at the pressures and temperatures that models place inside Neptune's mantle converts to diamond. That much is no longer a theoretical prediction waiting for experimental support. It is an experimentally supported fact, arrived at from multiple directions, consistent across different methods, and settled enough that planetary scientists use it as a given when building models of Neptune's internal heat budget and long-term evolution. The later steps, the The settling, the accumulation, the contribution to internal heating remain the open parts of the hypothesis, where the experimental data give way to modeling and the modeling gives way to honest uncertainty. The two major laboratory approaches rest in this scientific landscape like two survey markers on a map, each one placed precisely by careful measurement, with the territory between and beyond them still being filled in. The diamond anvil cell marks the static equilibrium behavior of carbon at high pressure and temperature, where the phase diagram says diamond is stable, and the cell confirms it. The laser shock system marks the dynamic formation behavior, whether diamond actually nucleates and grows on fast timescales in a shocked hydrocarbon, and the shock data confirm it does. Between these two markers, the hypothesis of diamond rain stands on firmer ground than it did when it was first proposed decades ago. From theoretical calculations alone, a laboratory in the middle of the night has a particular quality of stillness. The instruments do not rest. Exactly. They hold their calibrations, their vacuum systems run, their electronics wait in low-power states. The building hums faintly with the infrastructure that keeps the detectors cold and the lasers aligned. Outside, the parking lot is empty. The air is cool. Whatever stars are visible from that particular patch of ground glow at the distances they have always held, indifferent to the work that has been done in the building below them. Inside, the diamond anvil cell on its bench holds no sample tonight. The diamonds are parked apart, the tiny chamber empty, the pressure released, but the data from its most recent run exists somewhere in a storage system, on a server, in a paper waiting for review. The numbers in those data describe the behavior of a few trillion carbon atoms under pressures no natural process on Earth's surface will ever achieve. They describe what carbon does when the conditions around it match the conditions inside a planet that no human instrument has ever entered, and may not enter for decades more. What they describe is not a wonder imported from elsewhere. It is the ordinary behavior of ordinary matter, carbon, the same carbon that forms the graphite in a pencil, the same carbon in the organic compounds that build a cell wall, the same carbon in the methane that gives Neptune its deep blue tint, responding to conditions as it always responds, following the thermodynamic rules that govern it everywhere in the universe without exception. Under enough pressure, carbon becomes diamond. The experiments have confirmed this. The instruments have held it under their light and read the lattice spacing and found the rings. And somewhere inside Neptune, in fluid that has never been illuminated and will not be for a long time to come, the same thing is likely happening, slowly, quietly, in the dark. Carbon atoms released from their molecular bonds in the deep mantle, finding in the pressure around them the conditions that the laboratory instruments have measured and mapped, arranging themselves into the tight tetrahedral lattice that the phase diagram says they should. The process does not require a witness. It does not require confirmation from an instrument to proceed. It proceeds because the physics requires it to, in the same way that ice forms when water is cold enough, in the same way that a crystal grows when the conditions of its formation are met. The convergence of the two experimental methods, the quiet static precision of the diamond anvil cell, and the brief enormous energy of the laser shock system, arriving at the same result from entirely different physical approaches, produces a particular kind of calm. Not the calm of a question answered, exactly, but the calm of a question that has been approached from multiple directions and found consistent at each approach. The ground is not shaking. The measurements agree. What remains open is open not because the foundation is uncertain, but because the full building has not yet been constructed on it, and the construction takes the time it takes. In the meantime, the instruments continue their work. New experiments push the static pressure record incrementally higher. New shock experiments try mixtures of water and methane and ammonia rather than polystyrene, in the slow effort to make the laboratory sample look more like the real thing. New free electron laser facilities in different countries add their detectors to the accumulation of diffraction data. Each new data point falls somewhere on the carbon phase diagram, and each one that falls inside the diamond stability field at Neptune relevant conditions is another small weight on the settled side of the scale. The scale has been settling for a long time. The data keep arriving. The picture keeps sharpening without urgency, without drama, in the slow way that knowledge actually grows, not in the sudden illumination of a single finding, but in the gradual accumulation of consistent results from many directions, each one adding a little more weight, the picture gaining resolution, the way a long exposure photograph gathers light, slowly, in the dark, until what was invisible becomes clear. The laboratory bench is quiet. The diamond faces are parked. The parking lot outside is empty, under a clear and ordinary sky. Somewhere in the direction that Neptune sits, past the orbit of Jupiter, past the slow cold arc of Saturn's rings, past Uranus drifting in its tilted course, the blue world turns in its 165-year circuit, and inside it the fluid mantle presses inward toward its rocky core, and the carbon in that fluid responds to the conditions around it, exactly as the experiments say it should, in the dark, without witness, as it has for the full age of the solar system, as it will continue to do long after the last instrument in the building is switched off, and the parking lot is returned to whatever quiet the ground was keeping before the building was ever placed on it. Among the billions of stars that make up this galaxy, scattered along its spiral arms like grains of pale dust on dark water, planets circle in numbers too large to hold in a single thought. Not the large planets, not the gas giants with their vast hydrogen envelopes and their moons like small solar systems, but the smaller ones, the in-between worlds, the planets that fall below the mass of Neptune and above the mass of the Earth. These are the worlds that make up the most common category of planet in the galaxy, if the data from the great planet hunting telescopes is to be believed. For every bright, familiar Jupiter wheeling around a distant sun, there may be several of these quieter worlds, smaller, denser, richer in compounds of carbon and oxygen and nitrogen, tracing their slow orbits in the dark. Ice giants, the astronomers call them, not because they are cold at their surfaces only, but because so much of their mass is made of compounds that on Earth we associate with cold water, ammonia, methane, all of them compressed and heated and changed by the weight of thousands of kilometers of overlying material into something that is no longer quite any of the things those words suggest. Not ice, not gas, something in between, fluid and pressurized and strange. There may be hundreds of millions of such worlds in the Milky Way alone, perhaps more, each one a closed interior, sealed from observation, carrying its chemistry and its heat in permanent darkness. Neptune is the closest ice giant, the only one near enough that a spacecraft has ever passed through its system, and that only once, for a matter of hours, 4 decades past. Even at that distance, 4.5 billion kilometers from the Sun, it sits close enough in cosmic terms that the light it reflects reaches a telescope within hours. What lies inside it is a different matter. What lies inside it is, in the truest sense, unreachable. The interior of Neptune has never been crossed by any instrument. The pressures there would reduce any object to its component atoms, and yet the interior of Neptune is not beyond knowing. It sits in laboratories, approximated, pressed against diamond tips, struck by laser pulses Measured in billionths of a second, the evidence accumulates. The picture becomes more detailed with each passing year, though it is not complete and may not be complete within any human lifetime. The question at the center of that picture, the one that has waited 4 decades since a physicist first committed a calculation to paper, is whether carbon, freed from methane molecules by the crushing conditions of the deep mantle, forms diamond crystals that then sink through the planet's fluid interior in a slow, continuous, geologically patient rain. Not a metaphor, a physical process. One with consequences for how much heat Neptune holds, how its magnetic field is generated, how it compares to its near twin Uranus, and whether that same process is unfolding right now, at this moment, around other stars too distant to resolve into anything but a faint variation in brightness against the dark. That question is still open. It may be the most important thing about it. The Kepler Space Telescope spent 9 years staring at a patch of sky containing roughly 150,000 stars, measuring with extraordinary precision the slight dimming that occurs when a planet crosses in front of a star. From those measurements, and from the statistical analyses that followed, a picture emerged of how planets are distributed across the galaxy. Gas giants like Jupiter, it turned out, are not the norm. They are the exception, the most common type of planet detected by a significant margin. In some analyses, is the sub-Neptune, a world smaller than Neptune but larger than Earth, orbiting at a range of distances, sometimes close to its star and sometimes far. The TESS telescope, which followed Kepler and surveys a much wider portion of the sky, has continued adding to that census. Thousands of such worlds are now catalogued. Thousands more are inferred from the statistical patterns in the data. What this means is that the physics at work inside Neptune is not local. It is not an oddity confined to the outer edge of one unusual solar system. It is, in some form, playing out inside a category of world that may constitute the most abundant class of planet in the galaxy. Every one of those worlds that shares Neptune's rough composition, that deep mantle of compressed water and ammonia and methane, pressurized to conditions far beyond anything achievable on a planetary surface, is a candidate for the same chemistry, a candidate for the same interior rain. Each one sealed, each one dark inside, each one carrying, perhaps that slow continuous drizzle of crystalline carbon downward through the fluid toward a rocky core, releasing heat as it goes, warming the planet from within in a way that its star does not. The galaxy, seen in this light, is full of quiet, sealed cauldrons doing chemistry in the dark. Some of those worlds are more extreme than Neptune. Stars differ in composition from the Sun. The Sun formed from a cloud of gas and dust with a particular ratio of carbon to oxygen, a ratio that determined, in part, what molecules could form in the disk around it, and therefore what the planets that assembled there are made of. Stars with higher carbon to oxygen ratios than the Sun would produce planetary disks richer in carbon-bearing compounds. The planets that formed in those disks might have interiors so saturated with carbon that diamond does not form as a minor product of high-pressure chemistry, but as a dominant structural material, a mantle not of silicate rock, not of water and ammonia and methane, but of compressed diamond extending thousands of kilometers, the bulk of the planet's interior, a single, vast crystalline form. These hypothetical worlds have a name: carbon planets. They have not been confirmed by direct observation, in part because the data needed to characterize a planet's interior composition from the outside is difficult to obtain and rarely unambiguous. But the physics does not forbid them. The chemistry, on paper, allows them. A star with the right elemental balance, a disk with enough carbon, a planet that assembled in the carbon-rich part of that disk, and the interior that forms would look nothing like Earth, nothing like Neptune, but something more like the inside of a diamond anvil cell, rendered at planetary scale, a world whose very structure is the material that inside Neptune falls as rain. These are not nearby objects, they are scattered across distances that no instrument currently built could meaningfully probe. They are, for now, mathematical possibilities, outcomes permitted by the physics and chemistry of planet formation that may or may not be realized in the actual galaxy. But the tools are improving, the understanding deepens, and each step taken toward understanding Neptune's interior is also a step toward understanding whether those more exotic worlds are real. Neptune and Uranus sit side by side in the imagination of planetary science, near twins in size and bulk composition, close enough in their fundamental structure that models built for one are routinely tested against the other. They are the same kind of world, and yet they differ in one way that has no fully settled explanation. Neptune radiates roughly 2.5 times more heat than it receives from the sun. This excess, this internal warmth pouring outward into space, is the planet's own energy, generated somewhere within its interior. Uranus, by contrast, radiates almost no such excess. It emits about as much energy as it absorbs from sunlight, and no more. The two planets are nearly the same in composition, nearly the same in size, and yet one is glowing quietly with internal heat, and the other is not. This difference is a long open question in planetary science, and it is a question that the diamond rain hypothesis touches directly. If crystalline carbon is forming in Neptune's deep mantle and sinking through the fluid toward the core, the process releases energy. Dense material descending through a less dense medium converts gravitational potential energy into heat. The diamonds do not burn, do not glow, do not produce light. They simply fall slowly through thousands of kilometers of fluid, and in falling, they warm the planet. The heat produced would be real, diffuse, and continuous, spreading outward through the mantle over geological time, and eventually emerging from the planet's surface as the infrared radiation that telescopes measure. If this process is active in Neptune and not in Uranus, if the interior chemistry of the two planets has diverged in some way that sustains diamond precipitation in one and not the other, it would go some distance toward explaining why one planet glows warmly in the infrared and the other is, by comparison, cold. It would not explain it fully. No single mechanism is likely to account entirely for a difference as large and as persistent as the one between these two planets. Planetary interiors are complex, layered systems with many competing processes, and any explanation that attributes the whole of the difference to one cause is probably too simple. But the diamond rain hypothesis sits within the range of processes that could contribute. The heat it produces is real heat. The energy it releases is real energy. And the question of whether that process is ongoing inside Neptune, or inside Uranus, or inside both, or inside neither, remains genuinely unanswered. There is something useful in placing these two planets next to each other. They are, in a sense, a natural experiment, a pair of worlds similar enough in their fundamental properties that the differences between them may reveal something specific about which interior processes are active and which have ceased or which have never begun. To read that experiment, more data is needed, and for that, a spacecraft must return to the ice giants. The plan exists. It has been given the highest priority of any large-scale planetary mission by the committee that advises on the direction of planetary science in the coming decade. A spacecraft that would orbit Uranus, entering its system, circling it over years, probing its gravity, and magnetic field and atmospheric composition and interior structure with instruments far more sophisticated than anything carried by the Voyager that passed by 4 decades ago. The mission has not yet launched. The timeline stretches across years of development and years of travel. The spacecraft that would begin the journey has not yet been built, but the priority is assigned, the scientific case is made, and the work of designing such a mission is underway. What such a mission would return is not, in the first instance, a direct measurement of Neptune. Uranus is the closer target, the more accessible world, the one whose orbit makes a rendezvous more practical within the constraints of orbital mechanics and mission lifetime. But a spacecraft in orbit around Uranus, measuring its gravitational field to infer the density distribution of its interior layers, characterizing the magnetic field that its interior generates, analyzing its atmospheric chemistry and heat flow, would produce data that directly tests the models built for both ice giants. The interior models that predict where diamond formation should occur, at what pressure and temperature, in what abundance, are models that apply to Uranus and Neptune both. Data from one is a constraint on both. Evidence from Uranus narrows the range of what is possible inside Neptune, and vice versa. The picture that would emerge from such a mission would be the most complete portrait of an ice giant interior that science has ever assembled. It would not be the interior itself. No instrument aboard a spacecraft can see through thousands of kilometers of dense fluid to the crystallographic state of the material below. But gravity measurements reveal density layering, magnetic field measurements reveal the motion of electrically conductive fluid at depth. Heat flow measurements distinguish between a planet actively generating internal energy and one that has grown cold and quiet. Each of these is a piece of the puzzle. Together, in combination with the laboratory data that continues to accumulate, they build toward a picture that may, in the coming decades, be detailed enough to say, with reasonable confidence, whether the diamond rain model is correct, or to say that it is not, and that some other mechanism, or combination of mechanisms, better accounts for what is measured. That, too, is a real possibility. The models are good. The experimental evidence is real and reproducible. The physics allows the process. But a well-supported hypothesis is not a confirmed fact. The interior of Neptune has not been measured directly. The specific conditions at each depth, the exact pressure, the exact temperature, the precise chemical composition of the fluid at different layers, are estimated from models of planetary formation and evolution that carry their own uncertainties. The diamond stability field can be mapped in a laboratory, but placing that map accurately over the interior of a planet that no instrument has penetrated requires assumptions, and assumptions can be wrong. This is the calm truth at the center of the science. The evidence points in a direction. The direction seems clear, but the pointing is not yet the arrival, and the gap between them is not a failure of science. It is simply the honest distance between what is known and what is not yet confirmed. That gap is not empty. It is full of future measurement, future experiment, future missions crossing the outer solar system toward a blue ice world that has kept its interior private for the 4.5 billion years of its existence. There is a particular quality to scientific uncertainty at this scale. It is not the uncertainty of confusion, of contradictory evidence pulling in different directions. The evidence on the whole coheres. The theoretical predictions made 4 decades ago by a physicist working with the best tools available to him have held up against experimental tests that he could not have imagined when he made them. The laboratory data aligns with the theoretical picture. The observed properties of Neptune, its excess heat, its compositional data, its magnetic field structure, are consistent with the model even if they do not uniquely confirm it. This is not a state of bafflement, it is a state of convergence not yet complete. The picture is coming into focus. The edges are still soft. And that softness, that slight irreducible blur at the boundary of what is known, is part of what makes the subject restful to sit with, in the way that the night sky is restful to sit with. Not because it is empty, but because it is full in a way that exceeds any single mind's capacity to fully contain. There is always more there. There is always more interior, more depth, more silence beyond the reach of the instruments currently aimed at it. The specific world that anchors all of this, Neptune itself, is a point of blue light at the edge of the solar system. From the distance of Earth, it is not visible to the naked eye. Even in a modest telescope, it shows as a disk, only barely resolved, with a color that carries, in faint form, something of the quality of its atmosphere, that deep absorbing blue produced by methane at the cloud tops, pulling the red wavelengths from sunlight and releasing the blue ones outward into space. 4.5 billion kilometers of empty space separate it from the sun that illuminated it. Sunlight arrives there, weakened to about 1/900th of the intensity it carries at Earth. The planet is cold at its surface in ways that are difficult to render in ordinary temperature comparisons. A cold that is not the cold of a winter night or a mountaintop, but the cold of a world that receives almost nothing from its star and retains what heat it has from sources far below. And yet it is not entirely cold. It is warmer than it should be, given what the sun provides. That warmth comes from inside, from whatever process or combination of processes is at work in the dark interior, generating energy that slowly works its way outward through thousands of kilometers of pressurized fluid and eventually radiates into space. The source of that warmth is the question. The diamond rain hypothesis is one candidate answer. It may be the right one. It is, at the moment, among the most compelling ones, and it will wait with the patience of something very old and very far away for the instruments that will eventually be capable of addressing it more precisely. In the meantime, the planet continues. It has continued for 4.5 billion years without being explained, and the pace of its interior processes does not adjust to the pace of human understanding. The methane in its deep mantle is breaking apart under pressures that no surface instrument has ever reproduced entirely. The carbon freed from those broken bonds is doing what carbon does under the conditions that exist there, forming whatever structure the thermodynamics of that depth and that temperature dictates. If the models are right, and the laboratory evidence suggests they are at least pointing in the right direction, that structure is diamond. And if it is diamond, it is falling, not fast, not dramatically, but continuously over geological time, through darkness that has never been broken by any light. This process, if it is real, has been underway since Neptune's interior first reached the pressures and temperatures at which the carbon chemistry changes. That was not recently. That was billions of years ago, in the earliest epochs of the planet's cooling and settling, when the interior was even hotter than it is now, when the conditions for diamond formation may have been more widespread, more intense. The planet we observe today is not the same as the planet that existed when the process began. It has changed. It has evolved. The interior has stratified. The heat has slowly dispersed outward. The layers have settled into the rough configuration the models describe. What is happening inside it now is a continuation of something that has been happening for most of the life of the solar system, and it will continue. Not because the planet has any intention of continuing, it has none, but because the conditions that drive the process persist, and conditions drive outcomes, and the outcome of those particular conditions at those particular depths in that particular fluid appears to be the slow formation and slow descent of tiny crystalline structures made of carbon, each one a form that takes several billion years of planetary interior to produce, each one sinking through a darkness that will never be observed, settling eventually at the boundary of a rocky core that no spacecraft will ever reach. There is a kind of completeness in that. Not the completeness of an answer. The answer is not yet fully in, but the completeness of a process that does not require observation to proceed, that has been and will be and is now happening in a place entirely indifferent to whether it is understood. The universe is full of such processes. Chemistry unfolding in sealed interiors across the galaxy, crystals forming in darkness, heat rising slowly through dense fluid and escaping into space, planets cooling over billions of years, or not cooling, retaining their warmth through mechanisms that the species that evolved on a small rocky world nearby is only now beginning to piece together. The ice giant worlds that make up so much of the galaxy's planetary population are mostly unobserved, mostly unnamed, mostly unknown in any specific detail. They are statistical presences inferred from the patterns of light variation around distant stars, characterized in bulk properties at best. Their interiors are sealed behind layers of fluid and gas that no instrument can penetrate, at distances that make even the most powerful telescopes nearly blind to their details. What happens inside them is, for now, a matter of extrapolation from the one nearby example, from the laboratory data, from the physics that does not change across the galaxy, even if the specific configurations do. But the extrapolation is not uninformed. The physics that governs the behavior of carbon under extreme pressure operates the same way inside a planet orbiting a star 40 light-years away as it does inside Neptune, and as it does in the gap between two diamond culettes in a laboratory. Pressure and temperature and chemical composition determine what forms. The boundaries between those forms, the lines on the phase diagram that separate graphite from diamond, gas from fluid, stable from unstable, are not local rules. They are properties of carbon itself, of the fundamental quantum mechanical nature of how that element's electrons arrange themselves in space. Those rules hold everywhere, and so the picture built from experiments and from the single ice giant within reach has something to say about every such world in the galaxy, even the ones that will never be visited. This is what planetary science has become, in part, a way of reading the universe at scale, a way of taking what can be reached, a single planet, a few years of spacecraft data, a laboratory sample compressed between diamond tips, and building from it a model of what is happening in the billions of worlds that cannot be reached. The model may be wrong in its details. The diamond rain may be more abundant in some worlds and less in others. The exact pressure-temperature profile of a given ice giant interior depends on its size and composition and history in ways that cannot all be estimated precisely from the outside. But the broad pattern, ice giants of a certain composition at a certain mass and age, running this chemistry in their deep interiors, has a generality that extends beyond any one example. Neptune is the example closest to hand, the blue one, the cold one, the one that glows more warmly in the infrared than its composition and its distance from the sun would suggest it should, the one around which a single spacecraft swept decades ago and took its measurements in a matter of hours before continuing out of the solar system into interstellar space, the one that has been observed since from a great distance, in light that tells something of its surface and atmosphere, but nothing of the kilometers and millions of tons of pressurized fluid below the cloud tops. That fluid is still there, still compressed, still hot at its deeper levels, still doing whatever chemistry the conditions dictate. The methane is still breaking, the carbon is still moving. The process, whatever it is exactly, continues on its own timescale, a timescale measured not in years or centuries, but in the slow geological rhythms of a planet's interior, evolution, rhythms too gradual to observe directly, too deep to probe with any instrument currently in existence, but not too gradual to leave a signature in the planet's heat, its magnetic field, its bulk properties that can be measured from outside with sufficient care. The future of this science is a combination of patience and instrument. Patience, because the mission that would orbit an ice giant is years from launch and years from arriving. Patience, because the laboratory data is built experiment by experiment, each one adding a small increment to the map of what is possible at what pressure and temperature. Patience, because the statistical picture of the galaxy's planetary population is built observation by observation, each faint dip in a star's brightness adding one more point to a distribution that already contains thousands. An instrument, because each new generation of tool reaches a little further into higher pressures, into shorter timescales, into fainter signals from more distant objects, and each advance opens a portion of the question that was previously closed. There are good ideas and real evidence, and the patient accumulation of measurement from multiple directions. There is not yet confirmation. There may be in a few decades. There may not be if the interior of Neptune turns out to be more complex than the models predict, if the conditions at depth depart from what the calculations estimate, if some other process accounts for the observed heat in ways that do not require diamond formation. All of these remain possible. The open question is genuinely open. The answer is not hiding just out of sight, waiting to be retrieved. It is genuinely unknown, and the work of knowing it is real work, ongoing, incomplete. That incompleteness is not a shadow over the science. It is the science. The questions that are fully answered are, in a sense, the quiet ones, the ones that no longer need to be asked. The live ones, the ones that generate new experiments and new missions and new calculations, are the ones where the evidence is real, but the conclusion is not yet settled. Diamond rain inside Neptune is one of those live questions. It has been live for 4 decades. It will likely remain live for a decade or more to come, and in that time, the evidence will continue to accumulate, the models will continue to be refined, and the picture will continue to come into focus, slowly, in the way that all pictures of planetary interiors come into focus through the patient combination of what can be measured from outside and what can be reproduced in a laboratory. Never quite the same as the real thing, but close enough to say something true. The stars outside have been there since long before the first questions were written down. The ice giants circling them have been there longer still. The carbon inside those planets has been compressed and broken and reorganized since the planets first formed, in processes governed by the same physics that governs the interior of every laboratory apparatus built to probe it. There is a continuity in that, a sameness of physical law, spreading across distances too large to feel in any ordinary way, expressing itself in diamond crystals forming in the interior of a planet that receives the sun's light as a dim, distant point of warmth, barely enough to see by, barely enough to warm the upper clouds. Below those clouds, in the deep fluid that no sunlight has ever reached, the pressure increases with depth in a slow, unbroken gradient that reaches at the boundary of the rocky core, conditions that exist nowhere else in this solar system except within the interiors of the other giant planets. At some depth along that gradient, if the models are right, the conditions cross into the diamond stability field, the region of pressure and temperature, where diamond is simply what carbon is, not what carbon is forced to be, not an exotic exception to carbon's ordinary behavior, simply what it prefers, given the choice that the conditions at that depth present. And in that field, carbon atoms settle into their tetrahedral arrangement, one by one, forming structures that are dense enough to descend through the surrounding fluid in a rain that has no weather, no season, no variation by time of year, only the steady thermodynamic patience of a process driven by physics and indifferent to observation. Those crystals settle downward. They have been settling for billions of years. They will continue to settle long after the instruments that measure Neptune's heat output have been switched off, long after the mission that would orbit Uranus has completed its work and gone silent, long after the scientists who built those instruments and designed those missions and wrote the papers that synthesized the results have been gone. The planet does not require the understanding. The process does not require the witness. Neptune turns on its axis, tilted at a steep angle, its blue face catching a faint warmth from the sun. Its magnetic field wraps around it in the asymmetric tilted configuration that has puzzled planetary scientists since it was first measured, generated somewhere in the interior by some conducting fluid moving through some arrangement of heat and pressure that the models do not yet fully capture. Its cloud tops show faint banding and occasional bright patches of methane ice, the weather of a world whose dynamics are driven partly by internal heat and partly by the slow, distant influence of a sun that is little more than a bright star from that distance. And below all of it, in the permanent dark, in the fluid that is neither ice nor gas, at the pressures where chemistry becomes geology and molecules become crystals, something is falling, slowly, continuously, in silence,